Alright, hello everyone and welcome back to another video. So, we are in the process of learning integration by partial fraction decomposition. Okay, so with regards of integration, so far we learned how to integrate a decomposition with distinct linear factors, and we learned how to integrate a decomposition with repeated linear factors. Now it's the time to learn how to integrate a decomposition with irreducible factors. Okay, now the thing here is it's going to get a little bit challenging here. Okay, so we cannot focus on the decomposition in this video. So in this video and forward, I'm only going to focus on integration. Okay, otherwise the video is going to be super long. Now the integration here is really tricky. Okay, that is why I want to focus on integration. But I suggest you take this problem, try to do the decomposition by yourself, try to get these constants and make sure you know how to do the decomposition very well. Okay, all right, so we want to integrate this function and I have already given you the decomposition. First what we do is we write the partial fraction decomposition, right? Okay, so instead of integrating this function, complicated function, now we integrate negative 7 over x with respect to x plus 8x plus 1 over x square plus 1. We integrate that with respect to x. Now the first part, integrating this first part is easy, right? We already know how to do that. We can take that negative 7 out. We have to integrate 1 over x, and let's integrate this one later. Okay, let's wait a little bit. So if you integrate 1 over x, we get natural log absolute value of x. So that part is easy. Now we can focus on the other part, the part that contains irreducible factor in the denominator. All right, so let's go back. Let's talk about decomposition. Now we have a one key rule in decomposition, and I want you to digest this very carefully. Now, the way we do the decomposition is that we factor the denominator as much as possible. And for each factor, we will have a fraction representing in the decomposition, right? For x, we have a fraction. For x square plus 1, we have a fraction. So denominator, I mean, finding out the denominator, coming up with the denominators in the decomposition on the right-hand side is okay, right? It's straightforward. It's just we use the factors. Now coming up with the numerator in the decomposition, okay, so the way we decide these numerators is that, well, we make sure in the numerator we have a polynomial 1 degree less than the denominator, right? So that is why we have a first degree polynomial in the numerator here, okay, because we have a second degree polynomial in the denominator. So 2 minus 1 is 1, so that's why we have a first degree polynomial. Now this is a key relationship. Okay, now think about this. If we had an nth degree polynomial in the denominator in the decomposition, our numerator is going to be n minus 1th degree polynomial. Okay, so that's the relationship, 1 less than the denominator in terms of degree. Okay, so that's key in integration, trust me. All right, so how do we keep that in mind? So how do we integrate this complicated rational function again? It's complicated again. Now the key is, the technique that we use is integration by substitution. And the reason, okay, the reason to use integration by substitution lies with this relationship. Now let's try to understand this. It's crucial that you understand it. Now if you have been following my integration by substitution video series, we have a trick to find the substitute, trick to decide the substitute. So let's take an example, x times ex square. Now here the substitute u is going to be x square. Why? Because its derivative, remember I said in integration by substitution videos that once you decide the substitute, make sure derivative of that substitute exists somewhere else in the integral. So a derivative of x square is 2x. Forget about the constant, we can deal with the constant later. We do have x somewhere else in the integral. Then we said, well, we can comfortably do integration by substitution. That's a one rule, okay? One helpful fact that we can use in integration by substitution. Now think about this. Well, here I'm going to say my substitute is going to be x square plus 1. Now that's a second degree polynomial. What's the derivative of x square plus 1? It's 2x, a first degree polynomial. Now here's the thing. If we have an irreducible factor, okay, in the function that we want to integrate in the denominator, okay, so if we choose our u to be nth degree polynomial, if you choose our substitute to be nth degree polynomial, its derivative is going to be n minus 1th degree polynomial, right? Because when you differentiate an nth degree polynomial, you lose a degree, you get an n minus 1 degree polynomial. If you differentiate a quadratic polynomial, you get a first degree polynomial. If you differentiate a third degree polynomial, you get a second degree polynomial. So that's why this relationship is so crucial. So that your substitute is always going to be what? The denominator polynomial. Because it's going to be an nth degree polynomial and its derivative is going to be n minus 1, and that's going to be in the numerator. So we know that we can use integration by substitution. Okay, does that make sense? Digest that. All right. Okay, because that's not the end of this problem. All right. So we can always choose our u to be x square plus 1 here. Okay. All right, now let's write this problem somewhere else again. So we want to focus on this part, right? So I say my u is going to be x square plus 1. Perfect. Now if you want to do the integration by substitution, you have to take the derivative, right? So it's 2x. Now here comes another problem. Here's the most crucial part, okay? Now 2x, do we have 2x? Well, we have 8x plus in the numerator. We don't see an I to I, right? We expected to see 2x in the numerator, but we are not that lucky, okay? We have the right type of polynomial, right? Because our derivative is a first degree polynomial and our numerator is also a first degree polynomial. So, but we are not that lucky to get the exact same thing. So how can we manage this? Now the other thing is, why do we need this exact derivative here? We need that so that we can cancel out it, okay? If you do integration by substitution, you know that this du over dx term will help you to cancel certain terms in the integral in most of the problems. But do you see that 2x gonna cancel out anything in this 8x plus 1? No, right? 8x plus 1 is much different than 2x. Now what's the obstacle here? This is the crucial part, okay? So this is what I'm building up for. So what's the difference between 2x and 8x plus 1? The format difference is, the obstacle is this plus 1. Do you agree? I mean, if we just had, think about this, okay? If we just had 8x without that plus 1, then it would have been much easier. I mean, 2x, 8x, it's a difference of 4, difference of a constant. I mean, it's going to be okay. It's totally okay, right? It's almost the same thing. But that plus 1 is the obstacle. Do you agree? Can you see that? Okay, if you just had 8x, you can at least cancel out x. Think about this. Think about it. That's a good way to understand it. I mean, once you replace this dx by du, you will able to cancel out one of these x. And that's it. But can you cancel out x here when you have 8x plus 1? No, that plus 1 is an obstacle, right? Do you agree? Can you see that? Perfect. So how are you going to deal with that? Well, we use an algebraic trick. What is the algebraic trick? So what we are going to do here is, we are going to divide each term in the numerator by denominator. Listen carefully. Each term in the numerator will be divided by denominator. So what we are going to get is 8x by x over x square plus 1 plus 1 over x square plus 1. Okay, so that's what I did here. I divided each term in the numerator by denominator. Now the purpose of that is that, well, see here, we have that simpler form, right? 2x, 8x, almost the same thing. Can you see that? Can you understand that? Perfect. Now what we are going to do is, we are again going to integrate this function, this rational function here in 2 steps. So first let's integrate 8x over x square plus 1. Okay, I know it's a lot of things. So we are going to use integration by substitution here. Now dx is du over 2x. All right, so let's replace that here. So it's 8x over x square plus 1 is u, dx is du over 2x. Now can you see what I'm talking about? Well, see, boom, x gone, right? So 8 over 2 is 4, so it's 4 over u. Can you see that? If we had plus 1 here, we couldn't have done that, okay? So what is the, oops, du. I was overexcited. This should be not dx, du. Okay, so how can we integrate this? Well, we can take 4 out. Integral of 1 over u is 4 natural log u. Alright, so we are done with 2/3 of the problem. So let's go back. So we have one part of the answer, -7 natural log absolute value of x. The other part is 4 ln u, absolute value of u. But -7, what is u actually? Well, u is x square plus 1, and we can drop the absolute value because x square plus 1 is always going to be a positive number, right? So there's no need of absolute values. Perfect. But still we have a one part to finish because we have to integrate the small part 1 over x square, okay? Because remember we split the function. So how do we integrate 1 over x square plus 1 with respect to x? Well, if you can remember, it's easy. There's a rule. The rule that we often need here is that if you have a function that look like 1 over x square plus a square, the formula is, the answer is 1 over a times tangent inverse x over a. This comes up lot in partial fraction decomposition if you have irreducible factors. You cannot avoid that, so please memorize that. So here 1 is a square, so a is 1. So what is the answer? 1 over 1 tangent inverse x over 1, so which means it's tangent inverse x, right? Okay, so the what's left is tangent inverse x. All right, so now I want to summarize this. Okay, I want to summarize this in a better way. So what's the problem? So we had to integrate -7 over x plus 8x plus 1 over x square plus 1 dx. Okay, so we split that out. We integrate -7 over x with respect to x, plus we want to integrate 8x plus 1 over x square plus 1 dx. Okay, all right, so we knew the integral of -7 over x is -7 natural log absolute value of x, plus now what we did here is we split the rational function. We said that it's 8x over x square plus 1 dx plus 1 over x square plus 1 dx. Okay, now what we did is we integrated this part with integration by substitution. Why? Because u is x square plus 1, substitute is the denominator, and its derivative is almost same what you have in the numerator. So we cancel out certain terms with a great comfortability, and we use integration by substitution, and we got the integral for that part as 4 natural log x square plus 1. And we integrated this part using tangent inverse strategy. Okay, so what usually happen in a non-repeated irreducible factor problem, okay, it should be non-repeated. If it is repeated, don't even start that in this video. Let's do that in a separated video. It's terrible. But here, if you have a non-repeated irreducible factor, usually two things will be involved: integration by substitution and that tangent inverse thing. Okay, so at some point you have to split your fraction with the reducible factor. Okay, you split that. One part you integrate with integration by substitution, other part you integrate with tangent inverse rule. Okay, all right, so I have to do two more videos on this non-repeated irreducible factors, because I want to show you complications of these things. Okay, so yeah, so make sure that you digest this, make sure you understand it, and let's meet on the other video. Thank you very much.